Hello everyone. So today we are going to start with the prime numbers. I'll cover from the basic things from high school mathematics. Okay, so first what we'll do, we'll check for primality check. Okay, is the number is prime or not. First we'll do in O of n time block time complexity. Okay, here I'm considering that you have basic knowledge of C++. You know how to use STL, vectors, maps, etc. things, and that's it. Okay. Then after, okay, you also familiar with the notations. Okay, time complexity notations and space complexity notations. So first we will check a number in O of n time complexity. Then we'll try to do optimize it in O of square root of n time complexity. And maybe in this video I'll cover the sieve of Aranthesis, okay, formerly known as sieve, okay. It is also used for primality check, and it takes around time complexity of n log of log n, okay. So first we'll start with the what are prime numbers, okay. Most of I think everybody knows that, okay. Let's consider we have a number n, okay, a number n, okay. So we can say n is prime, okay, if only 1 and n are the only divisors of that number, okay. It can be only divided by 1 and itself, okay. And there's another notation also, that like we can say like every prime number can be denoted as 6k plus minus 1, okay. I'll tell you how, okay. Let's consider a number n, okay. It can be shown as 6k, okay, or 6k plus 1, or 6k plus 2, or 6k plus 3, okay, or 6k plus 4, or 6k plus 5, okay. 6k plus 6 means what? 6 into k plus 1, okay. So here I'll write that, okay. 6k plus 6 can be written as 6k plus 1, which can be also written as 6k dash, which is same as this thing, okay. So now we have to remove the numbers which are not prime, okay. See, 6k is divisible by 6, 6 2 3, okay. We'll remove this. Then 6k plus 1, okay, we are not sure about this, okay. 6k plus 2, we know that 6k is already an even number, and adding 2 is also in is a even number, okay. So for any k greater than, okay, here k is greater than 0, okay. If k is greater than 0, okay, for any k greater than 0, 6k plus 2 will be an even number and will be greater than 2. So this is also not a prime number. 6k plus 3, okay, 6k is already divisible by 3, plus adding 3 is also divisible by 3. So this is also not a prime number. Then 6k plus 4, yes, it will be divisible by 2, at least 2. If not 4, at least 2. Okay, so this is also. Now we have 6k plus 1 and 6k plus 5. Okay, can we make this 6k plus 5 as 6k minus 1? Let's do it. Okay, so what we can do, we say that 6k dash plus 1 is another notation, and here k dash is equal to k minus 1. So it will be 6 of k minus 1 plus 5, 6k minus 6 plus 5, which is 6k minus 1. Okay, so okay. So for another k, we can show that 6k plus 5 will be 6k minus 1 for another k. Okay, so now we proved that 6k plus minus 1, with 6k plus minus 1 we can show any prime numbers, okay. Now what we'll do, we'll move to the checking prime numbers. Okay, now we have to check a number is prime or not. Okay, what we'll do, uh, let's take 7. Okay, 7 number. So what we'll do basically here, um, I think you know modulo operator. Okay, modulo operator in any computer language, like in C++, we use percent sign to show modulo operator. Okay, if I'm doing an modulo k, which means that after dividing n by k, whatever remainder will remain. Okay, we can get that by doing this operation. Okay, n modulo k. Okay, so if I have to check 7 is divisible by any number x, the condition we need is 7 modulo x should be 0. Okay. Now we know that any prime number is divisible by 1 and itself. So the numbers remain are between this 2, 3. Okay. We have to check on those number. So start with the 2. So 7 modulo 2 will be 1. 7 modulo 3 will be 1. 7 modulo 4 will be 3. 7 modulo 5 will be 2. And 7 modulo 6 will be again 1. Okay. So we can see that there is no number which completely divides 7. So we can say that 7 is a, okay, prime number. Okay. It's a prime number. But now we have to do it, okay, in code. Okay. So what we can do, uh, we'll code in C++. Okay, I'll code in C++. Okay, uh, we'll code it. Okay, let's start. Okay, here I'm using LL for long long. Okay, so what we can do in this code, we are going to just do a primality check. Okay, like int n. I'm taking input for n. Okay, now what I have to do, uh, I have to check how many divisors are there. Okay, I can take count equal to 0. Okay, so what I can do, for int I equal to 1 less than equal to n I plus plus. Okay, I can do loop through over 1 to n. Okay, or even 2 to n, n minus 1. Okay, okay, we'll make changes. Okay, we'll make changes. Okay, so first, if and modulo I equal to 0, what we'll do, count plus equal to 1, will increase count by 1. So if count equal to 2, we'll print cout yes prime. Okay, and else cout no, not a prime. Okay, let's check our code. So first what I can do, 1, no, not a prime. Yes, 1 is not prime, it's working. Okay, 2, yes, prime. Another 29, yes, prime. 99, yes, not prime. Okay, it is working. It is working for, let's 40, yes. Okay, what we did, we know it only divided by 1 if it's prime. Okay, it can be divided by 1 and n only. Okay, so if we have count as 2 of divisors, then we can say yes, it's prime. Okay, now the changes I want to make is, we'll start from 2 and till go n minus 1, and if it is divisible. Okay, so we'll print out here. No, we'll print this out here, and we'll break. We don't need count here. Okay, we don't need count. Let's try. So 1. Okay, now it's showing 1 as a prime. Okay, we have to handle this case. Okay, handle this case. Okay, if n is equal to 1, control C, control V is 1, not a prime. 2 is a prime. 5 is a prime. 99 is not a prime. Okay, 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 okay. Instead of break, we'll return from this function. Okay, now 99. Yes, it's not a prime. 97. Yes, it's prime. Okay. So what we did here, we know that it's only divisible by 1 and n. So we made a loop from 2 to n minus 1. As we can see here, the condition is I is less than n. We are going till n minus 1 only. And if there exists any number which divides n, it means that it's not prime. The n number is not prime. Someone is dividing it. Okay. So we printed no, not a prime, and written from this void function. Okay. And after loop we handle one case. Okay, for 1. Okay, 1 is not a prime. Okay, so if n is 1, we said no, not a prime number. Else, yes, it's prime number. Okay, now we'll try to optimize this. Okay, okay, so now what we can do, the current whatever we did. Okay, we look from 1 to n. Okay, the time complexity was O of n. Okay, it was linear time complexity. Okay, now we have to optimize it. What we can do, let's try what we can do here now. Okay, let's consider we have a number n. Okay, and we can denote it as q into d. Okay, so what's the maximum bound q and d both have? Okay, both can have. Okay, it can be root n into root n. Sorry, why I did 2. Okay, root n. Okay, root n into root n will be n again. Okay, so root n will be such a number which will be the higher bound for any divisor. Okay, I'll take an example. Okay, we did in our school math, in school so many times we did. Okay, like we have a number like 35 and we need all divisors of 35. Well, what we used to do, we used to write them in a pair. Okay, pair of multiplication, like 35 can be written as 1 into 35, 5 into 7. Okay, let's take another number. Okay, this is too small, but we can do. Okay, let's take 40. Okay, 40, we have 40. What we can do, we can write it as 1 into 40, then 2 into 20, then 4 into 10, then again 5 into what? 8. Okay, then 8 into 5. Okay, and now you can see 10 into 4. After this they are getting swapped. Okay, they are just getting swapped. So what we know now, that we have to check for this upper half only. Okay, only this upper half, because in this lower half they are going to get repeat. Okay, so what we can do now, we have to just observe. Okay, this was the loop. Okay, we started, this was the loop, and we went till 5 only. Okay, so what is root 40? Root 40 will be around, okay, 6 square is 36, so it will be some 6 point, okay, something 6.6 point dash dash, okay. So if we even made a loop till 6, it covers 5, okay. Like if we go 1 to 6, it will check for 1, okay, for 2, for 4, for 5 also, okay. So in square root, we can find out that a number is prime or not, okay. Even one of them divides that number, it means that it's not a prime number, okay. Okay, except this thing, okay, we don't need to check with 1, okay, because even prime number is divisible by 1, okay. We'll try to code this out, okay. Okay, so int n c in n, okay. Now what we know, we have to check from 2, okay. We are not going to check for 1, okay. We are going to check from 2 to square root of n, okay. Let's do it. For int I equal to 2, I is less than equal to square root of n and I plus plus. Okay, why we are doing square root till square root of n? Like in last example, what we saw, 40, okay. What was the square root of 40? Around 6 point something, okay. And 5 is less than 6, okay. So some people will say that no, we don't have to check that point square root of n, we have to just check one less than it, okay. But let's consider a perfect square number, okay, like a perfect square number, like mm, let's say 9, okay, 9, okay. So what is square root of 9? It's 3, okay. So people will say that no, we have to check just before square root, and then what, for what will we will check, we will check for just 2 only, okay. And will not check for 3 if we made this condition, okay, this condition, okay. It will work for all n who are not perfect square, okay. This code will work. We are just checking I is less than square root of n, but a number is perfect square, okay, and it is a square of a prime number, okay. Then we will miss that prime number, okay. We will miss that prime number, and again the code will give yes, it's prime for a number which is the square of prime, okay. Here 9 is square of 3, okay. So square root of 9 is 3, and we are not checking till 3, okay. And 3 is the only one divisor of that 9 except 1 and 9 itself. So this can cause problems, so we have to go till square root of n equal to, okay. So same here, if n modulo I equal to 0, we are going to print prime, and we are going to return from this function, okay. And here we are going to print not prime, okay. Yes, we have to check condition for n equal to 1, okay. If it's 1, it's not prime. Yes, no, here condition will be not prime, and here we'll print out as a prime, okay. I'm not taking 1 as an input, okay. You already know that we have to separately handle this case, okay. I'm not writing it down. So 2, yes, it's prime. 23, yes, it's prime. 96 is not prime, okay. This code is right. What we can do, like actually people don't use square root of n, okay. Like why? The return type of this square root of n is double. Yes, and sometimes a floating point error happens. Okay, for large n, it's possible that it will be giving a wrong answer. Okay, so what people do, so many times we write condition like this: I into I less than equal to n. Okay, it's the same as we are checking that I is less than equal to square root of n. Instead of square rooting that n, what we are doing, we are squaring I and checking the condition. Okay, you can write in this way also. Okay. Okay, time complexity is O of square root n. Here we can do that. Okay, okay, I'll just rub this down. Okay, now what we did, our loop was for one, no, yes, it was from 2 to square root of n. So the time complexity is O of root n, and time complexity is square root. Now, what we can do, we'll try to solve some problems. Okay, we'll go on some platform and try to submit it. Okay, okay. What we'll do, we'll solve this problem. Okay, this is from Geeks for Geeks. Okay, here we have to check the given number is prime or not. Okay, if it's prime, we have to return 1, and if it's not prime, we have to return 0. So what we'll do, we'll first a linear code, okay, linear time complexity code, and then we'll do with the square root time complexity. Okay, so what we'll do, for int I equal to 1, no, we'll go from 2, I is less than n, and I plus plus, if n modulo I equal to 0, will return, what will return, return 0. Okay, and after loop, we know that nobody is dividing that n. Okay, here we have to do capital N. So we'll return 1. Okay, and another case is if n equal to 1, return 0. Okay, let's try it. Okay, for a given test case, it's giving line, right? Let's submit it. Okay, runtime error. It's saying time limit exceeded. Okay, now we know that it's not supporting linear time. Okay, what we'll do, we'll try to optimize it. Okay, see, here number are 10 raised to 9. Okay, if you have already have an experience in doing problem solving, you know that you can't do a linear time. You can't use any algorithm or couple of algorithms which are taking linear time if the given test range, okay, whatever range on which you are doing anything. Okay, if it's 10 raised to 9, you can't do it in linear time. Okay, you have to do it in either square root of n time or log of n. Okay, or O of 1. Okay, linear time doesn't work here. Okay, so what we have to do, we have to change our code. What we'll do now, if I into I is less than equal to n, we know that we have to check just till square root of n. Now we have to check that other cases are also covering it. Yes, it's covered already for one. Okay, let's try to submit it. Okay, yes, you can see that it passed all the cases. Okay, okay. Now we'll we'll try to do some changes in this code. Okay, see, uh, few minutes ago, uh, I talked about how we can show any prime number in the format of 6k plus minus 1. Okay, now how can we use that in our code? Okay, now see, we have to work on k. Okay, we don't know its value. Let's consider we have k is 1. So we consider we have two numbers we are getting from, and one is 6k minus 1. So it will be 5 and 2 will be 7. If it's 2, we are getting what we are getting 6 to the 12 and minus 1 11. Okay, and then 13. If it's 3, we are getting 17 and 19. As you can see, we are covering all prime numbers. Okay, we are covering all prime numbers with this. So we know that if an number is dividing by some x number, okay, this is 0. Okay, x can divide n, and we know that x is not a prime number. Okay, if this x is not a prime number, so we know that x can be shown as a prime factorization of some prime numbers. Okay, see, let's say x is 20. Let's say 20. Okay, so 20 can be shown as 2 into 2 into 5. Okay, we can say 2 raised to square into 5. Okay, in this format we can show x if it's 20. Okay, so if number is can divide 20. Okay, so it is also it also get divided by this prime factors. Okay, this is simple logic. Okay, we can say like that. If n divisible by x is 0 and x divisible by y is 0, so we can say that n divisible by y will also be 0. Okay, this is simple maths. So now from this thing, from whatever we just did here, what we can do, like what to what conclusion we can reach from this. Okay, so the only thing remain here, that to check a number is prime or not, we have to just check there exists another prime number less than that number which can divide that n or not. Okay, so we have to check for x which is less than n, and x belongs to the sets of prime numbers. Okay, this thing we have to check. Okay, so what we'll do, we'll run a while loop. We'll take uh, a, a k starts from 1. Okay, from that k we'll make these two n1 and n2. Okay, and we'll check, we will do primality check first, like that n gets divided by this number or not. And if this and 2, okay, and to get exceeds from I, like, okay, this is n2. If n, okay, I'll write somewhere, okay, okay, n2 into n2 is greater than equal to this n number, okay. This is our breaking point, like we are, in this case we are checking till square root, okay, the same we did in last time, okay. I'll code it. So let's code here, okay. Let's code here. Now we'll handle the base case, okay. If n equal to 1, return 0, okay. Now int k equal to 1, okay, and we'll run while loop of, okay, while always true, and we'll put some breaking condition here. So first n1 is 6 into k minus 1, okay. Yes, the things we are missing here is 2 and 3, okay. This rule only follows for prime numbers greater than 3, okay. Like here you can see, uh, okay, see here, this part, you can see it starts with 5, then 7, then 11, 13, 79. So what are we missing? We are missing 2 and 3, okay. These two numbers we are missing. So let's try to cover them up, okay. So if n modulo 2 equal to 0, or n modulo 3 equal to 0, return 0, okay. This condition we can do like this, n equal to 1, okay. Only one if to check them all, okay. Now int n2 will be 6 into k plus 1, okay. If n modulo n1 equal to 0, or n modulo n2 equal to 0, like any of this exists. So what we are doing, return 0, okay, because it's not prime number. Now we are doing k plus plus, okay. And another condition, what we talk about, if n2 is greater than, okay, n2 into n2 is greater than what, the main n, will break from this loop, okay. And here will return 1, that it's prime, nobody divided it. Let's check. Okay, output difference. Your output is 0. Hmm. What just happened? Okay. K is 1. Your output is 0. It should be 1. Oh, okay. Okay. Yes. For 5, what's happening? For k equal to 1 itself, okay? Itself, it's okay. In the first loop, we can see that n2, what n2 will be? N2 will be no, n1 will be 6k minus 1. Okay, k is 1, so n1 will be 5. So here n1 is 5, and here what we are doing, we are checking does n modulo n1 is equal to 0, and we are doing return 0. So we are checking 5 is divisible by 5, okay, and with that we are deciding that Okay, this code is saying that this is not prime number. Okay, but here we are checking 5 by itself. Okay, so we have to handle these conditions also. So what we can do, mm, how to simplify it? We don't need to add so many if conditions. Okay, our code should be like, we should make it simple. Okay, let's try. We'll do here. Okay, if n into n minus 1 is greater than equal to n, let's break it. Okay, now we have to check. Okay, last time I talked about 9. Okay, so 9, for 9 we have to check for just 3. Okay, okay, this thing will get covered here. Okay, in this line we'll cover this thing. Let's take 25. Okay, 25. 25 is not prime, but it is divided by 5, which is prime, and 5 into 5 is greater than equal to n, and for that we are breaking it. So this condition is not going to work. Okay, we can do, we will do here. Okay, we'll check a condition. Okay, where n1 and n2 are not equal to the main n. Okay, n1 is not equal to n, and n2 is not equal to n, and they are divisible by either one. Okay, so it's written 0. Let's check it. Let us submit it. Wow, on the first test case, what is the difference here? Your code's output is 1, its correct output is 1, output difference 1. Wow. Okay, why? Hmm. Seriously? Okay. Why? It doesn't make any sense. The code's output is 1, its correct output is 1, output difference is 1. Expected output is 1. Okay, your output is, your output is, okay, leave it. Okay, I don't know what's problem here. Okay, let's see this code. Okay, see this code. You'll understand what we are doing here. Okay, we know that A prime number which is greater than 3 can be shown as in the form of 6k plus minus 1. Okay, so we are just checking for 2 and 3 separately because we can't form them with 6k plus minus 1. If n equal to 1, okay, 1 is not prime number, return 0. Okay, this line is clear. I hope yes. Now we are starting with k equal to 1. Okay, and 1 is 6 into k minus 1 and 2 is 6k plus 1. Okay, if n1 is not equal to n and n2 is not equal to n. Why we are checking this? Because for phi, okay, n1 was phi and it was checking for itself. Okay, a prime number divides itself. Okay, because in this code we are, after doing that check, after that we are checking, does we have to break, does we have reached the limit of square root. Okay, but here already we reached the limit of square root. Okay, if we are checking phi number, okay, to check the is it prime or not for number phi, we already reached the last number. Okay, so to handle that case we added this, and 1 is not equal to main and 2 also is not equal to n. Okay, then we increase the k. Okay, and here the last case we have to break after some time. Okay, so we already know that just till the square root of that number we have to check. So what we did, if we are till n2, okay, I checked n2 into n2 is greater than equal to n, break. That's enough. Okay, let's try this code. Let's try this code. Okay, control C. I don't know why GFG is not giving the answer correctly. Control V. Okay, print n, C n. Okay, instead of written, what we are going to do, we have to print. Okay, we are going to print. So C out not prime. Okay, and let's return from here. Okay, here also same thing, C out no prime, and here C out it's prime. Let's see. Okay, so first one not prime, two, why 2 is not prime. Oh shit. Okay, yes. This thing we miss. Okay, if they are gets divided by these numbers, then okay. Okay, now it's messed up. Okay, see, control Z. See, what was the problem here? Here is checking 2 modulo 2 equal to 0. Okay, and yes, 2 modulo 2 is 0, but 2 is a prime number. It's checking for itself. So we have to add another condition. If n equal to 2, or okay, we have capital N, or n equal to 3, same thing, control C, control V, and return. Let's see, 2 it's prime, 99 is not prime. Let's use big number, 1 and 2 3 4 5 6 7 8 9, not prime. Okay, another number 97, it's prime. Okay, now you can see that this code is working. Okay, this code is very fine. Now what's the time complexity here? Let's check. Let's check. So basically what we are doing for any number, okay, what are we doing for any number n? Okay, for any number n, we are just checking till square root of n, and we are not even going till square root of n, huh? We are even in this square root of n, we are just checking for prime numbers. Okay, prime, my bad handwriting. Okay, okay. So prime numbers till square root n. Okay, we are checking only for those. So the time complexity is like square root of n by 6. Okay. Oh, and okay, this is very big difference. Okay, between this and this, because square root of n already uh, already reducing the time complexity by root times. Okay, root times. So see, like this, if you have 25, so for 25 we are just checking 5 times. Okay, if it's 625 we are just checking for 25 times. Okay, square root. And even by dividing by 6, see, this was already a small number and we are dividing by 6, like around 4 times. Just we check for 4 or 5 times. See, so I think this much is okay for today. We'll go in advanced topics like sieve. Okay, we'll try so many problems which are related to sieve. Okay, so that's it for today. Thank you for watching this. Bye.